This video is for lesson 1.6, modeling with equations. So this is, again, review of Algebra 2 and Algebra 1 to prepare for our pre-calculus course. There's guidelines for modeling, and it's just how we approach a modeling problem. And a modeling problem is kind of another way to say an application or a worded problem. So in the modeling with equations, what first thing we're going to do is read a whole situation. And in that, we want to identify the variables, what is the problem asking us to find, as well as what are the other quantities and things going on in the problem. We need to then translate the words into algebraic equations and expressions so that we can make sense of the problem. We're going to set up the model. Sometimes that includes drawing a picture, doing something so that we can see what's crucial and what is needed to do the solving. And then finally we solve and then ask ourselves, does that answer make reasonable sense? Is that viable in this situation? Okay. So here let's look about problems about interest. So we have a problem where Ben is investing some money at 4%. He's also going to invest other money at 5.5%. At the end of 1 year, he wants to look at both of those accounts and look at all the money he earned and say, was that 4.5% of the total amount invested? Well, how much did Ben invest? Well, we'll talk about that in a second. We need to understand the concept that the interest that you would have gotten over the course of a year, just the interest amount, would be the principal, the amount you invested times its annual rate. So if we just had this one account, we would take $4,000 and multiply by 4%, and that would give us how much interest we made in 1 year in this one account. In the second account, we don't know how much Ben is investing, but so I'd say X, and we'd do that X amount times 5.5%, and that would tell me how much interest Ben earned in the second account. We would take those two interests from the two accounts and add them together in this problem. So we want to know that when we add all that up, that we're going to have the total amount that was invested, not just 4,000, but 4,000 and the other account X, and find out, was that indeed 4.5% of the total amount invested. So we're saying we have our principal A and our principal B, the amount we put in to the first account plus the amount we put into the second account is going to give us the total amount that Ben invested, okay? And that's 4,000, and that's X, and so this is going to be 4,000 plus X, okay? Taking this amount, we're multiplying it by 4%, which is 0.04, and this amount, we're multiplying it by 5.5, which is 0.055, and we want to know if we add those together, does it equal the total invested times 4.5%? Well, now it's just an algebraic equation to solve for X. And we solve for X and we say, oh, the amount that and X stood for how much Ben put in the 5.5% account. So Ben would have to invest $2,000 at 5.5% to earn 4.5% of the total investment. One of the keys to note is this was a worded problem. Your answer is in words. It's not just say X equals 2,000. Nowhere in this problem did it say solve for X. It's asking you a very specific thing, and so we're answering it in words. All right, area, length. This requires you to remember formulas that you have from your past. This is what your geometric formulas for area, perimeter, sides of right triangles, sides of everything. So here we have a flagpole, and it has guy wires. Guy wires are wires that are staked to a pole to keep the pole from falling over in one direction or another. And when we've done this, we have this flagpole. It created what it says is an isosceles triangle, which means that all three sides are the same length. Okay. It tells us this, that it's not isosceles, that it's equilateral, and equilateral means all three sides the same length. And we're going to say, okay, the two guide wires are what we're interested in. So since we want to figure out the length of these guide wires, I'm going to call them x, which also means this base down here is a length of x. And the flagpole, being straight up and down, meaning perpendicular to the ground, is going to divide this one equilateral triangle into two right triangles, where each part of the base here is 1/2 x, so each side is that. Okay. Now this is very much like a geometry class. We're saying, oh, here's the height of the pole, which I don't know, but if I just look at one of those right triangles, there I've got that, and we look at that and say, ooh, we know the Pythagorean theorem. If I want an equation for height, I would take the hypotenuse squared, I would subtract this other leg squared, so 1/2 x squared, and then take the square root, and that's going to equal the height of this right triangle. Okay? And we have, when we simplify that, we get √3/2x. Now, it was given in the problem that the height is 5 less than the guide wire. So I know that since this is height, √3/2x, then it has to equal the height, which is 5 units less than the guide wire, 5 feet less than the guide wire. Now we have an equation to solve, so we're going to get all of our x's on one side and our constants on the other. Have that. Then we're going to divide by that coefficient, and we have that. Simplifying it and putting in our calculator, since this is an application, we would write this in an approximate decimal answer, and we have approximately 37.32 feet is the length, or the height. Oh, sorry, we found the length of the guide wires. The length of the guide wires. Oh, and we had to convert it to inches because it said in the problem, do it to the nearest inch. Okay? Okay. Mixtures. So here's a problem where you've got 2 buckets of acid. One bucket is 50% acid, and the other bucket is, it says pure acid. That would be 100% acid. So one of your buckets has 50% acid, and the other bucket has 100% acid. We're going to mix a certain amount of each, and we're going to get a quantity that is now at 60% acid. It tells us that we used 300 milliliters of the 50%. We don't know how much pure acid, and we don't really know how much 60% we're going to have either. But we can set this up and say, 300 we know, x we don't know, so the final amount is 300 plus x. The 300 is 50%. The x is 100%, and we want this final amount to be 60%. Multiplying this all together on percents, we have to move the decimal, so 0.5, 1, 0.6, and then we have our equation. We get all of our x's on the left, and we have our constants on the right. We just isolate our variable. We divide by our coefficient, and we say, oh, the amount of 100% acid needs to be 75 milliliters. Now we need to write that in a sentence, and so we need 75 milliliters of pure acid to add to 300 milliliters of 50% solution, and then we'll have a total of 375 milliliters of 60% solution. Here's another problem about mixtures. This one says a pot contains 6 liters of brine, concentration of 120, and this is grams per liter. Okay, how much water should be boiled off? So we're going to subtract to increase the concentration to 200 grams per liter. All right, so let's write this down. How much sodium in 6 liters of 120 grams per liter? Well, 6 liters times 120 grams per liter means we have 720 grams of sodium. How many liters of 200 grams per liter solution to have a 720 grams? Okay, I want to re-explain this a little bit better. We have a bucket of solution, and in that bucket has water and 720 grams of sodium. We figured that out by figuring out by the concentration how many grams of sodium there are. When we boil this solution, we will not lose any of the sodium. We will still have 720 grams of sodium, but we will have less water. If you have less water, it's increasing the concentration. It's going to become saltier water. It's going to, like if you tasted it, it would taste saltier. And it's because you have less water and the amount of sodium. So if we're going to have, if we had this original amount, 6 liters, we had 720 grams of sodium. And if I wanted a solution of 200 grams per liter, this is the concentration I want, and I'm using this much sodium, how much water would that take to make it this concentration? So we say, okay, we have 720 grams. We divide it by the 200 grams per liter, and that's going to tell us that if we had 3.6 liters of solution with 720 grams, we would have this concentration. But what are we starting with? We are starting with 6 liters of water. And if we have 6 liters and we want to boil it down to 3.6, how much would we need to boil off? Well, we just subtract. And we say, oh, you need to boil off 2.4 liters of water, and then you will have the proper concentration. So to reduce from 6 liters to 3.6 liters, you would need to boil off 2.4 liters, and then you would have a concentration of 200 grams per liter. Okay. All right, this is about doing a job. So we have these two people. We have Stan and Hilda, and they're going to work together to mow a lawn. And when they work together, it takes them 40 minutes. What we want to know is, basically, we could say how much time if just Hilda was mowing the lawn, how much time if just Stan was mowing the lawn. In the end, they ask us about Stan, but this is idea that we don't know how long it takes either one of them on their own. We just know that when they work together, it takes 40 minutes. The other thing we do know is that Hilda works faster than Stan. If Stan took an hour, Hilda would only take half an hour. If Stan took 2 hours, Hilda would only take 1 hour because Hilda works twice as fast. All right? So let's look at this problem first of all. How we think of jobs and work. Well, Stan can do one job in what I call Stan minutes. However long it takes Stan to do it. He does one job in a certain number of minutes. So I call them Stan minutes. Okay? And Hilda can do one job in Hilda minutes. Now I could use like the variable S and the variable H here for Stan minutes and Hilda minutes. But we're just going to write it with words right now. And we do know that if we add those two, not the fractions, well, we will be, but if we have the two of them, Stan and Hilda, working together, they're going to be able to do one job in together minutes. And we know that together minutes is 40. All right? So this becomes an addition. These two are working together, and it's going to equal 1 over 40 minutes. One job in 40 minutes, their rate. We also know, we had this in our previous lesson, you can't just say 1 over S plus 1 over H equals 1 over S plus H. That does not work. That is not true. It's not a true statement. So we have to look at this in a different way and say, oh, let's write these as the difference of Stan minutes and Hilda minutes. So if we gave Hilda the variable of X, well, Stan is always going to have twice those minutes. Because remember, Hilda works twice as fast. She's faster. So if she did something in 1 hour, Stan would take 2 hours because he's slower. So this is this thinking it through my variables, how I'm going to do this. We could have said, give Stan the variable, and then we'd have to say Hilda was 1/2 of whatever that is. I don't want a fraction, so I did it this way. So I'm going to say 2x equals Stan minutes, and x equals Hilda minutes, and I'm going to rewrite this equation in that way. So I'm going to have 1 over 2x for Stan, 1 over x, let's see, 1 over 2x for Stan, and 1 over x for Hilda. This is how long it takes, and it's got to equal 1 over 40, and we're going to solve this problem. How do we solve? We got fractions. We multiply by the least common multiple of the denominators, so we no longer have fractions. And then we add that up. We go, oh, x equals 6. Oh, it takes Hilda 60 minutes. And if it takes Hilda 60 minutes, then it takes Stan 120 minutes, otherwise known as 2 hours. So, working alone, it takes Stan 2 hours to mow the lawn. Distance, rate, and time. And always remember DIRT. Distance equals rate times time. So in this problem, two cyclists are 90 miles apart. And they start riding towards each other at the same time. One of them cycles twice as fast as the other. So again, one of them would be cycling at like x, and another would be cycling at 2x. Who is faster? The faster person is the x. The 2x is the slower person, okay? So we have the first one, and the faster one, and then the slower one. And if they meet 2 hours later, so they are both cycling for 2 hours, what is the average speed in each cyclist is traveling? Because they obviously were not going the same speed the whole way. We're just going to look at their average speed. Well, cyclist A is going to go some distance d. They're meeting, and they're not both going 90 miles, but there is a distance that will have been traveled that's 90 miles when they meet. Because cyclist A will have gone one part of the distance, and cyclist B will have gone the other part of the distance, and then when they meet, that would have covered the entire 90 miles. So, cyclist B is going to do 90 miles minus whatever cyclist A went. So for cyclist A, we have their rate times their time, and it equals their distance. Distance equals rate times time. Cyclist B is distance equals rate times time. So we have each of their equations for this, and we're saying, oh, D is, because this equation tells us what D equals. It equals 2x. So since D equals 2x, and over here we have 4x, we have an equation. We just add 2x to both sides, divide by 6, and we have the rate that the cyclist A is going. We now know x, and then we know that the other cyclist is going twice that. And so the cyclist, because it asks for if they are 2x, what is the average speed of each cyclist? I'm sorry, I think I only answered this with one of them. The first cyclist is, I don't have it here. One of them is 15 miles per hour, and the other one is twice that, which is 30 miles per hour. And that's the end of these applications.